Unit 2 Summary. In Unit 2, we learned how to represent motion in 4 ways. We learned how to represent it in words, with a motion map, using a position versus time graph, as well as using a velocity versus time graph. Now, when we have a position versus time graph, if there's just going to be one single slope where it does not change, we can use this general equation to represent the entire mathematical and graphical relationship. Position is equal to velocity times time plus our starting position. And to save us having to write out the whole thing every single time, we use the following variables. A lowercase x represents horizontal position. A lowercase v represents velocity. A lowercase t represents time. And for the starting position, we have the lowercase x to represent our position. And that 0 to the bottom right indicates it's the position at time 0, or our starting position. Now, our velocity, we can calculate that from the slope of the line on a position versus time graph, where instead of using y2 minus y1 over x2 minus x1, we're using this in real world terms, where on our y-axis are our positions, which is why we have x2 minus x1, our position 2 minus position 1, and we divide that by the change in our times, time 2 minus time 1. Now, you can also represent motion using a velocity versus time graph, which we see below. Now, on a velocity versus time graph, the curve itself represents the velocity in that time interval. For this positive velocity, that indicates in those first 3 chunks of time, the velocity is remaining constant. And then in these last 3 chunks of time, the velocity is also remaining constant, but it is now a negative velocity. We can actually calculate the displacement, or the change in position, from a velocity versus time graph. That can be calculated from the area between the curve and the time axis. That's actually why I have shaded in over here on the left. That is the area between the curve and the time axis. We can also write that as this equation. Area, which is that area, which is going to be the same thing as our displacement. It's going to be the height of the area, which is our velocity, times the width of the area, our time. So we represent displacement, or the change in position, with the Greek letter delta here, this triangle, that tells us change, and the x indicates horizontal position. So displacement is the change in horizontal position here. That's equal to our velocity and our time when they are multiplied together. Our average velocity, which can be the velocity in a given time region, is going to be our displacement, or the change in position, over our time, or the change in time. Now, this is going to look very familiar from the position versus time graph up above, but it's just going to be the equation for the slope of a line. Now, speed is going to be a little different. Average speed, it doesn't matter your displacement, that change in position. What it depends on is our path length divided by our time, or our distance traveled over our change in time. In order to find that, look at each region of the graph and figure out the total distance traveled. In each region, you're going to add those distances up until you get to that final distance. All of them added together is going to be our path length, and you divide that by the time interval in order to figure out the average speed, or the change in distance, the distance traveled, over time. Now, one of the ways that we represented motion was with motion maps. Now, we had that summary that we included in our lab notebook about the 4 hints for drawing motion maps. I have rewritten those right here, as well as included an additional one that will help us moving forward. So the first one, each dot indicates a time. If a time is not written, assume each dot is 1 additional second. And the first dot, no matter what your time intervals are, will always be 0 seconds. Each time is going to be placed on the motion map at a position the object is at that time. 3. An arrow is attached to the dot and points in the direction of travel. The length of the arrow is relative to the velocity. What that means is the longer the arrow, the greater the velocity. Or really, the greater the speed in that direction. 4. Ensure a logical flow for your motion map. Now, as long as you are labeling those dots with the times and you are having the arrows point in the direction of travel, it should indicate a logical flow, which makes the motion map easy to follow. However, if it's a big motion map and things get cluttered together, it's going to be a bit hard to read. So make sure that it's going to be as easy to read as possible, because the point of a motion map is to be able to interpret the motion of an object and figure out where it is at a given point. Now, what I also added to this last little bit about motion maps is, moving forward, we want to ensure that each arrow, each velocity vector, is labeled with the letter V. That's going to indicate it is a velocity vector. As we start to work with more and more types of vectors, it'll be important to label what each type of vector is. Now, the rest of the Unit 2 summary is going to be practiced with displacement from a velocity versus time graph. Now, this is copied from up above with the same example of our velocity versus time graph, as well as our written description. The displacement, change in position from a velocity versus time graph, can be calculated from the area between the curve and the time axis, or area is equal to displacement, which is the velocity times the time. But before we even start worrying about our velocity versus time graphs, I would like you to consider the following scenario. An object travels to the right at a constant velocity of 2 meters every second. So our velocity is going to be 2 meters every second. Question 1. How far does the object travel after 1 second? Well, one thing that we can say is, if we know that we are traveling at 2 meters every 1 second, if we travel for just 1 second, we will have traveled 2 meters in distance. And because this is going to be a positive velocity, that will also mean that we would have a change in position of positive 2 meters. Question 2. How far does the object travel after 2 seconds? Well, if we are still traveling 2 meters every 1 second, but now we travel for 2 seconds, we are going to double that distance traveled, and we will end up with a total distance traveled of 4 meters. How far does the object travel after 5 seconds? Well, we're still traveling at that same velocity, 2 meters every 1 second. Traveling for 5 seconds means we'll have traveled a distance of 10 meters. Question 4. Explain how you determined the answer to problems 1 through 3. Well, what I was doing was I was showing my work in each of these problems, where I was using a little bit of our proportional reasoning that we talked about back in Unit 1 to show that my units canceled to figure out my final distance traveled, or, because we're using velocity, that change in position. So, using dimensional analysis, or our proportional reasoning, the change in position could be determined. Now, these first 4 problems, where we're just looking at that scenario of an object traveling at a constant velocity of 2 meters every second. Now, for these 4 problems, this is just a way for us to try to logically reason with what the relationship between velocity and time could be, and what that means for determining the distance traveled. Now, we're going to look at this another way. gain more practice with velocity versus time graphs. That's going to be on the next page. So once again, at the top, I still have our explanation of how we can calculate displacement from a velocity versus time graph up in the top right. However, what has changed in this problem is going to be our velocity versus time graph. This is now representing an object traveling at a constant velocity of positive 2 meters every second. So I took the previous scenario and I graphed it with a velocity versus time graph. Now for this problem, there's going to be 3 looking at the exact same time region. Now, assuming that our math here works out the same, where the area is indeed equal to that change in position or displacement, our answers for these next 3 problems should be the same as for the previous 4, really. So, problem 1, calculate the area of the shaded in region. So, we have the shaded in region here from 0 to 1 seconds and from 0 to 2 meters per second for our velocity. So if we're looking at the height of the region, I can write down that the height is going to be our velocity, which is 2 meters per second. What is the width of the region? The width is going to be our time, and that will be a time, well, specifically a change in time of 1 second. So my area is going to be equal to my height times my width, which is going to be equal to 2 meters per second times 1 second. So my area is 2 meters. Now, for the next region of the graph, problem number 2, we're now looking still at our height, which is going to be a velocity of 2 meters per second, but now we're looking at our change in time, that time interval of 2 seconds. So our area here will be equal to 2 meters every 1 second times 2 seconds, which will be 4 meters for our displacement, or that's change in position. And for problem number 3, calculate the area of the shaded in region. Well, now we're looking at it from 0 to 5 seconds. So while our velocity is going to be the same, 2 meters every second, our change in time is now 5 seconds. So our area is going to be equal to 2 meters every 1 second times 5 seconds, which is going to be 10 meters. Now, in each of these 3 regions of the graph, where we calculate the displacement from a velocity versus time graph, those should correspond to our answers from the previous part where we were just looking at it using proportional reasoning, where in the first 1 second of travel, we traveled a change of position of positive 2 meters. In the first 2 seconds of travel, we had a change in position of positive 4 meters. And in the first 5 seconds, we had a change in position of positive 10 meters, which is going to line up with our displacement method by looking at the area between the curve and the time axis on a velocity versus time graph. Now, this last problem is going to be more of an example where we can try to get practice with a more complicated way of looking at velocity versus time, where we now have a changing velocity. Instead of having 2 meters per second for the entire time range, we are only going to have it for the first 3 seconds. Then it changes from 3 to 6 seconds to a velocity of 0 meters per second. And then finally, from 6 to 10 seconds, we have a velocity of minus 3 meters every 1 second. So, for problem 1 on this back page, calculate the displacement from 0 to 3 seconds. Well, so I'm going to be looking at this area up here. The height of this region, our velocity, is 2 meters every 1 second. Our width of this region, that change in time, it's going to be our 3 seconds minus our 0 seconds, which is 3 seconds total. So our displacement, that change in our position, that's equal to 2 meters every 1 second times 3 seconds. So our change in position, the displacement for the first 3 seconds, will be 6 meters. The second region of the graph, from 3 to 6 seconds, well, that's going to be right here. The height of this region, well, it looks like the height is just staying constant, where our velocity here is going to be 0 meters every 1 second. Our change in time, the width of this region, 6 seconds minus 3 seconds, so this is going to be a 3-second time interval. Our change in position is going to be equal to 0 meters every 1 second times 3 seconds of travel. So from 3 to 6 seconds, the change in position is 0 meters. And finally, in the last region of the graph, from 6 to 10 seconds, the width of this region, the height of this region, our velocity, is minus 3 meters every second. The width of this region, our change in time, we end up at 10 seconds, we started off at 6 seconds. Our change in time is 4 seconds. So the displacement in the last 4 seconds of this graph, or the last 4 seconds of this object's motion, minus 3 meters every 1 second times 4 seconds. So the displacement, minus 12 meters. So this object travels to the left 12 meters in these 4 seconds.